Good morning, everyone. Sorry, we're starting a few minutes late. We're waiting for folks to show up. My name is Tashi. I am working. I'm working for Apinic. With me here, I have Paresh Bhai from Nokia. He's here because he pretty much helped us develop all our materials for SDN. We also conduct simple SDN workshops, 3-day, 5-day workshops, and Paresh Bhai actually helped us. So it's really good to have him here. If you have questions, maybe I can redirect it to him. So today's session it's a very simple look at how we see SDN. We are not saying we have that's the way or that's the correct way. All we are saying is based on what we see out there in the industry, and given the limitations of modern networks and modern equipments, we see today's talk is a look at what we see is viable as opposed to what we would ideally like. So that's what this talk is about. We will look at how routers have evolved from the early days of internet to what it is today. We will look at the very motivation for SDN, how it came about. Maybe I'll let folks settle in. Okay. We will look at OpenFlow. We will look at different SDN architectures, most of which are abstract. We will look at some use cases, and we will do a simple OpenFlow demo, right, at the end. So, routers. Even though I didn't work during the early days of internet, I have been in this industry only, 13, 14 years. But I believe early day routers also did these two same basic functions, right? Primary job is to find a path to a destination, and based on that, you actually forward packets to the destination, right? So those were what the early routers did. And the modern day routers, even though they're very complex, their basic functions are pretty much this too. So in terms of functionality, routers from the early days to what it is today, I don't think the functionality-wise it has changed much. But then here is a look at modern day routers, right? Even though the basic functions do not seem to have changed, has not changed, the routers are more complex, very expensive from a user's point of view. But the functions are still the same, right? And the reason for that could be, in the early days, we were carrying, the applications that the network was carrying was very simple, right? Simple text-based emails and stuff. And then all of a sudden, without anyone realizing, internet becomes the default communication medium for all of us. So massive new complex applications that are carried over this network. So what that required folks to build in so many different capabilities to support this many new applications over the network, right? You have management tools, you have high availability features built in, you have multiple services layer that get built into the router, you have complex QoS mechanisms that get built in, you have specialized hardware for specific network functions. Even though the basic function is still finding the path to a destination and forwarding packet to a destination, the routers have ended up becoming quite complex and very expensive again, right? Here is a quick look at the different planes, because we'll be touching on these things quite a bit throughout today's session. Control plane basically to have that intelligent look at things, to find a path to a destination, right? Good thing about the control plane is whatever protocols we run at that level needs to be interoperable, right? BGP implementation on Juno OS needs to talk to iOS too, right? So in that way, it's good, because even though different vendor implementations have different tweaks to it, but they are still interoperable, right? Backwards compatibility. We can't just say the older one is not good, kill it totally. Instead, you build upon what is already there. right? The problem is here on the data plane, right? Based on the decision that the control plane makes, whatever, when we actually forward the packet, it actually happens down there, down at the hardware level, and this is where the problem starts, because it's a closed system, right? Vendors don't seem to open it up, okay? And vendors wouldn't want to open it up because I guess that's where the differentiating factors come between their devices and other devices, right? And we have the management plane, right? The most common ones we use CLI and SNMP at the moment. But how did we even get here in the first place, right? How did our routers end up becoming so complex from instead of just doing the two basic functions that a router is supposed to do? And I believe it all boils down to the way we handled problems. You have a big complex problem, you try and build it into small manageable chunks, right? So the concept of maybe divide and conquer, right? So instead of me going head on and trying and tackling a very complex problem with a single solution, I try and break the problem into smaller pieces, and then I try and tackle the problems that are manageable, smaller pieces, right? And that was built on an end-to-end principle, meaning I distribute intelligence to the edges. I just don't have a central intelligence core and then I have dumb edges, right? Instead, if we look at modern devices, intelligence is embedded on almost all the devices that are in our network. So that intelligence has been pushed to the edges, right? It had its own advantages, of course. Now that it's spread out, the intelligence spread out to every network device, it's easier to scale, right? Instead of me building one big, massive intelligence node, I distribute that intelligence across different devices in my network. So it is easy to scale. And in terms of resiliency too, instead of a single point of failure, which could be if I have a big intelligence central box, that could end up becoming a single point of failure. So when you have this distributed intelligence in every node in our network, so it helps, right, in terms of resiliency. Second one is backwards compatibility, right? I don't think we can afford to turn off the internet and say, this thing is not good, let's try something new and better, right? Those days maybe it was possible during the early days when we were not even born, right? Few people were running the network. It wasn't that popular. Now that it's so popular, everyone uses it. I don't think we can afford to do that, right? In the early days, some of the protocols that we don't even know, NCP, Network Control Protocol, when that got replaced by the TCP/IP, I think people could replace it off directly without much issues. But in the modern day, I don't think we can do that. So no way that we can have a flat day, right? So instead, what this has forced folks to do is bring in incremental changes or incremental improvements to solve a problem, right? On top of what we already have, keep making improvements on top of that, right? So that was backwards compatibility. And of course, no one would have thought that the internet that we have would be used as the primary means of communication, right? So it's a victim of its own success, as people say, right? And then, of course, the need for higher performance. The need for higher performance is, I guess, what forces maybe most vendors to actually have a tighter coupling between their control plane and their data plane, right? Ideally, separating them is not difficult, but what sort of performance can you get out of it? So that has forced vendors, I think, to have more and more tighter coupling between their control and data plane, right? And all these things leads us to what we have today, very complex, expensive routers, right? So with that as the background, we'll look at the Clean Slate project. So some researchers from Stanford University, right? They had problems trying to, when they were doing the research, how me as a researcher, how do I even try out new protocols that I might want to test on existing devices, right? They started off with two primary questions, right? with what we already know today, how can we redo or how can we rethink what the internet is, right? How do we redesign? And that's taking into account how will the internet look from now, 15 to 20 years from now, right? They set out on a mission to reinvent the internet, I suppose, right? So one of the flagship projects out of the Clean Slate project was the Internet Infrastructure, OpenFlow, and SDN, the Software Defined Networking Group, right? There was a paper out in 2008. So this, I think, even though it may not be the most ideal way of doing things, it may not have the capability, but it still, that idea still gave birth to all the change in thought processes that we see today, both from vendor side and from researcher side, right? So it actually kicked off what's called the SDN revolution, right? So that was the problem that they were trying to solve. How do I run or test experimental protocols on existing devices? Because trying to do it on devices that you come up with, you lack performance, right? But trying to do it on vendor devices, they have hidden so many things that we can't really play around. So that's why they wanted something that would give you the required performance, as well as come up with a compromise. Maybe even the vendors could come to a compromise where even if you don't open up every hidden aspect of your device, at least open up certain interfaces through which we can manipulate certain things in the device, right? So how do we influence the forwarding behavior of a device, right? So this is how modern devices look like. We have a forwarding plane, we have the control plane, they are nicely tightly coupled, right? And that's how we manage to achieve the performances that we want, right? The control plane, like we discussed, primarily responsible for making intelligent decisions on how to reach a destination. That pretty much populates the forwarding table. The forwarding table pretty much responsible for forwarding the actual packets. So what they did was they wanted an abstracted view of the flow table, take out the control plane out of the device, right? So they wanted decoupling between control plane and data plane. This was a compromise, I suppose, because we do realize that it's not fair to ask vendors to open up everything for us to program. So it was a fair compromise where take out the control plane out, even though vendors may not let me program everything on the device, at least give me an interface, or if I can take out the control plane, at least I can program that and push down flows into the device, right? So it was a compromise. So what was the solution? The solution was actually a compromise, right? I take out the control plane. The control plane actually talks. The control plane actually talks to the data plane through a secure channel, right? And the control plane actually pushes flows down into the device's data plane, right? So how does it work? So the control plane or the OpenFlow controller is primarily what it can do is it can either insert new flows, it can modify existing flows out there in the flow table on the data plane, or it can delete flows, right? And here is an example of a very simple example of how a flow table might look down there on the data plane. You have matching header fields against which you match, and based on that match, you can act upon the matches, right? Example for flow 1, whatever the header field matches. Initially, when OpenFlow started off, the header field matches were pretty fixed, rigid, just 12 tuples. So matching against any of these headers, then we can define actions. Let's say if it's ingress port this, forward it out to port 1/1, right? So it's match and actions, right? So the controller pushes flows down to the data plane. Whenever a packet comes in, the forwarding table pretty much works the way it works. It looks up for matching flow entries in the table. If there are matches, It'll act based on the action that was defined for that match, right? It could be as simple as forward to port this port, or you drop the packet, or you send it up to the controller. So the separation of the control plane from the data plane is good, gives you a certain degree of way to manipulate the forwarding table, right? But what's the point of me just decoupling the control plane from a data plane of a device, right? If I have 100 routers, I could end up with 100 control planes that I decouple. So that's why the true the true power comes in when you decouple all these control planes from all these devices, and then you centralize them, and through one controller you start managing different multiple data planes, right? So that was OpenFlow. Because I put this intentionally here because even myself, when I started reading about these things, for me OpenFlow was SDN. Turns out it is not, based on my interaction with folks. So initially, yes, OpenFlow, people thought it was OpenFlow meant SDN, but now we realize that it's a part of it's a part of a bigger architecture, and OpenFlow is just one of the protocols out there. All right. But I think we should give credit where it's due. I think they started off this revolution. But what are the implications? So OpenFlow, they came up with this idea to decouple the control plane from the data plane, and that's one of the major implications, right? And that gave us that flexibility to actually manipulate forwarding tables without without the vendors actually having to open up lots of their hidden features, right? And I think the power comes in consolidating and centralizing the control plane. Like we saw before, instead of decoupling control plane from 1,000 routers and having them all separate, consolidate them, centralize them, and then now you see the network as if you look at it from an abstract view, you see your network as just ports maybe, and then your controller can then push flows down to your network, right? Initially, the correspondence between your data plane and in our modern devices, the association between the control plane and the data plane is 1:1. But with OpenFlow, now we can have 1:many, right? You have one centralized control plane, which can actually manipulate or push down flows to multiple data planes, right? But it's not without its own problems, right? Trying to decouple control plane away from the data plane, scalability is a major problem, right? Currently, we have control planes distributed on each device. So take all those things away, then and centralize them. That centralized controller needs to be beefy enough to handle that many data planes in your network, right? So scalability could be a major problem. Reliability, right? Currently, one router failing in my network does not necessarily bring down my whole network because we have distributed intelligence, decision-making processes across the network, right? But we take away that intelligence away from the box, try and centralize it. If that box fails, so it becomes a major problem. So we end up with multiple controllers that we need to maintain. And because of reliability, when we want multiple controllers, now consistency could end up becoming a problem. So if I have multiple controllers, they all need to have the same state information, right? They need to be consistent. With that, so like we just discussed, it was not their goal to actually separate the control plane away from the data plane, right? It was a compromise that they had to come to, the OpenFlow team, right? Because, like I said, I don't think vendors any day would want us to be able to program everything we want on their devices. So it was a good compromise, I think. Vendors didn't have to open up, yet we as users, we could still manipulate things, right? And that's where it allowed us to actually manipulate things, program things the way we want. Certain features that may not be there in vendor implementations, maybe we could push those new features ourselves instead of waiting for vendors to roll out those features, right? But the term SDN itself was actually coined by a journalist, it seems, who was a technical journalist who was actually writing a paper. So SDN do not necessarily seem to be a technical. It's anyway. We will look at other aspects. So OpenFlow was a starting point, definitely. It allows us to have a different thought process, right? OpenFlow. But I think this is where we need to be a bit, because there is no way we can decouple everything away, decouple the control plane functions totally away from the data plane, right? For the sake of performance. The reason current nodes perform better is because of tighter coupling. And we want to take this away, fine, we have taken that away. But if the performance takes a major hit, then what have I achieved, right? So I think there still needs to be some features or control functions that still need to be down there on the device, right? So being realistic, I think, is also important. As a researcher, I think, yes, people might want to rethink things and do things in a very simple and a manner they want, but reality is also important. I don't think vendors will open up things easily to us, right? So I don't think it's because last 20, 30 years, our routers from those early, last time I was looking at a photo of the first IMP routers. It's massive. It looks like a power unit with heavy heat sinks and stuff. From that to what we have now, incremental changes that have been made, right, by the community and by the vendors themselves. And for us to say, all right, let's throw all those things away, I think it's a big ask. So I think it's really, I think we need a compromise, right? So what's the SDN architecture today? So with that as a background, I think even I have met a couple of ISPs who have deployed SDN in their network, and it's a compromise. They have not gone vanilla SDN network, right? They have used existing features, existing tool sets, and there is a compromise, right? Because for you to take everything away, then you need to build all the intelligence or all the features that the industry has built for the last 30 years into your centralized controller, right? And it's a big ask. So SDN architecture today is more a hybrid sort of model, right? You still leave certain functions, control functions on the device itself, and yet you have that means of manipulating states on the device the way you see fit. So it is a compromise, right? Many different models out there, but every model has simple goal. Agility, right? That flexibility for me to have flows the way I want it and be able to modify or manipulate things the way I want it, right? Data plane and the proportion of centralization of the control plane. Today's model, I think it's all tightly coupled in our today's network. OpenFlow wanted a clear separation, right? And the hybrid approach, which we feel is viable, would still have certain functions still on the device itself, yet you still have interfaces which allows you to manipulate things. Right? With that, let's try and define SDN. I don't think I'll be good at this. The Open Network Foundation says there needs to be physical separation of the control plane from the data plane, right? Too narrow, I think, right? What have we achieved by just decoupling the control plane away from the data plane? It achieves nothing, actually, right? Whereas SDN, from as an end user, as someone who operates a network, SDN should give us that agility and flexibility. And how do we get that, right? So SDN is a new approach to networking that should give us that agility and flexibility, right? And that can be achieved through programmability and open interfaces. At the moment, the only open interface I have to configure my devices are the CLIs that the vendors provide. Right? Can I have something more than that? Right? Disaggregation and abstraction. Disaggregation, taking something that's closed and big and try and break it into smaller manageable pieces, right? Which is achieved through abstraction. If my network is, let's say from Bhutan Telecom's perspective, if my network is 200 routers, maybe I can abstract that network and look at it as one single router with 200 different ports, right? So with that abstract view, now it's easy for me to define flows. I could say from this port to send it out to that port instead of me having to program each and every router in my network, right? And of course, centralization of network control. So like I was mentioning earlier, no point in achieving decoupling if I have to decouple everything and maintain them separately. So the power comes in when we manage to decouple everything, centralize it, and from that one controller we start managing every node in our network, right? So that's centralization of network control with real-time network visibility. I think this is really important, network visibility. All these new things that people seem to push, it's all good. The idea is really good, but I think network visibility for me as a controller to make decisions in my network, I need to have a view of the network. Right? And how do I get that visibility of my network? How does the controller know how your network is connected to be able to make good decisions? Right? So that is also, I think, equally important. So with that, what are the objectives, right? Agility. Me not being constrained by limitations, right? Me being able to push things quicker, faster, provision services faster. Automation, everything that I do manually now, can I do it better? Right? Can I make my work that much easier? Right? Not so sure about CapEx and OpEx, I'm not even going to talk. Programmability, right? That kind of agility and stuff achieved through programmability, which is again achieved through being able to abstract the network and let network applications see it from an abstract view, right? And then, of course, the centralized control. Here's a list of SDN, SDOs, the IETF. The IETF is there, ONF, Open Network Foundation, MEF folks, they are also there. The Broadband Forum is there, ITU. But let's look at the general framework or architectures that people have proposed. Right. This is ITU's attempt at what SDN should look like or how SDN should be. Very abstract, right? Not much details, but the idea is there. I think you have your network resources, which are your actual physical devices in your network, right? They talk to us. They talk to SDN controllers. Could be one or could be multiple controllers, right? Of course, they have not defined how I interact from the controller down to the devices and stuff, but the idea is there, right? So they have defined what's called the resource control interfaces. Probably those are your southbound interfaces down from the controller to the devices, right? And then you have the network application sitting up there who would actually program your controller, and then the controller would manipulate or instruct your network resources, right? The idea is there from ITU's point of view. This is IETFs. IETFs is a bit more detailed, a bit more, I think it is a bit more doable, I guess, right? The same three layers, you have the application plane sitting up there, you have your control plane sitting there, and you have your actual data plane, right? You still have your data plane functions there, forwarding plane functions there, but they also define a new plane called the operational plane, primarily to operate the device itself, right? And they also propose separation of the control plane and the management plane, right? Management plane would be everything to do only with operating the device itself, right? Whereas control plane would be more to do with network functions, right? And then there is the network services abstraction layer, right? And I think this is really interesting compared to the ITU one, because now you're looking at being able to provide an abstract view to the network applications, so that network applications can then, based on that abstract view, network applications can actually directly manipulate the flow based on how the application wants it, right? So a much, much more interesting framework compared to the ITU one. And this is us giving it a try based on the existing tools that are there, based on existing technologies that are there, right? We also follow something very similar. You have the data plane with, again, hybrid data plane. Maybe I need to rephrase this: hybrid data plane, where you still have some control function sitting there. You have your control plane, and then you have your application plane, right? Again, very similar to the ITU one, the IETF one. Northbound interfaces up to your network application, right? On the data plane, this is the compromise that we were talking about. There is no way we can take away all these functions up there from day one. I think we still need to keep certain functions down there, and then maybe find a way to manipulate those functions that are sitting there, right? From route selection point of view, you still have ribs and fibs sitting down there on your data plane, but now with standard protocols like into the routing system, I2RS. So our devices, modern devices, they all maintain state information, right? You have the ribs, which are pretty much populated by the routing protocols, and the entries in the rib actually helps me populate my fib, right? And which actually forwards the packet. So I2RS, it actually allows me to inject states into the routing system without. So this is, I think, a good compromise without taking things away. All I do is, if I want to manipulate a forwarding state, then I manipulate the state on. I inject a state that I want, on-demand state that I want, onto the routing system, which will manipulate the forwarding behavior, right? And then from traffic engineering point of view, we have RSVPT, and you have segment routing, right? Segment routing is, I think there are lots of talks going on in this conference about segment routing, where me as a head end, I'm allowed to decide which path a flow needs to take, right? And those are based on segments. I treat the network as segments, and I, as the head end, I get to decide and say that, all right, I would like this particular flow to take this particular path, right? So that sort of traffic engineering can be achieved through segment routing. RSVPT, I think everyone is aware of it, right? And then that traffic engineering control engine that sits on the control plane will talk to those traffic engineering functions that sit on our device itself through path computation element protocols, right? Path computation protocols. In terms of resource management, because me as a controller, for me to come up with flows and inject those flows into a data plane, I also need to understand what resources are left on the device itself, right? And that can be achieved through IPFix, right? Flow information export, where traffic profiles or traffic information, basically this protocol that defines how traffic flow information or traffic profile can be sent or transmitted from an exporting device to a collector, right? And your controller now acts as a collector. Based on that profile information, it understands what resources are already used, what resources are available. So it helps it make intelligent decisions, right? Then from management point of view, you can rely on existing tools, SNMP, right, to manage the device itself. And based on the decisions that it makes, it needs to configure. But before that, I think topology discovery and management is more important. For me as a controller to make any decisions about my network, I need to have a view of the network, right? I need to know how my network looks like. And that one can be achieved not by coming up with something very new, but by just modifying the BGP protocol, right? BGP LS, BGP link state, where the network's link state information or the topological view can now be carried in BGP as a separate NLRI, right? So we are not redoing or redesigning everything. Instead, we are making or adding features onto existing protocols, which gives us the features that we would like. So using BGP LS, your controller is able to have a view of a topological view of the network, right? Once I know the network, once I know what resources it's using, once I know what kind of traffic engineering needs are there, then making a decision becomes fairly simpler for the controller, right? And to configure the flows onto the data plane, we can use OpenFlow, right? If have OpenFlow protocol running there and keep pushing flows down into the data plane. And OpenFlow now, since version 1.3, it also has nice, nice pipelined features. So OpenFlow can also be leveraged. We will show you a real example where this architecture is at work, right? Or you could use the netconf model, the protocol, right? So it allows me to manage a device or configure a device or retrieve or update configurations on the device through open APIs, right? Netconf. And the language which we use to do this is the Yang model, where I can model data in the form of a hierarchical tree, where your nodes have names and values, or it could also have the relationship between those nodes, right? So all those information is modeled using the Yang, and that actually helps netconf manage the device. So when you push your configurations down onto the device, right? So that's on the southbound, right? On the northbound, pretty much the standard, even in the IETF even in the ones that are proposed by IETF, the northbound, how your controller now interacts with your network applications or network-oriented applications is through open interfaces, right? Mostly through REST-conf. So SDN does not necessarily seem to be a revolution, right? It's more evolution. We are still working on improving the network. It's an evolution. I don't think it's going to be possible for a while to have a single protocol and say this is SDN, right? I think there will always be compromises. Researchers can say whatever they want. This is what I have. Research is ideal, right? You run a lab, you don't have customers connected to your network, you can come up with any idea you want. But when you're operating a network, I come from Bhutan, originally very small, but the king is also my customer, right? So I can't really mess up things in my network. So what I want is a separate thing, but what I can do is also separate. So there needs to be a compromise, I think, between these two things, right? So instead, I think different technologies, different features, different tools need to come together for us to be able to achieve what we want, unless we shut down everything and maybe redo everything. Right. So definitely no one protocol that defines SDN, right? Rather, it's a mixture of protocols and technologies that enable us to centralize the control functions, look at networks from an abstract view, and then allow us to manipulate or modify things the way we see fit or the way we want, right? So with that, in current networks, if I elements, path computation elements, maybe my network is SDN capable. I could say that, right? Because I have managed to have a traffic engineered path which does not necessarily follow the default path, right? If I implement OpenFlow to push certain flows into my network, I could say my network does some form of SDN, right? If I can configure them using netconf or using the Yang model, I could still say that my network is SDN capable. So the idea here, I think, is I don't think there is one protocol out there after implementing which I can say I have a SDN capable network. So I think it's a mixture of everything. This is a quick aside. SDN versus NFV, because Paresh Bhai is here. He'll be doing an NFV tutorial from tomorrow, right? So we thought maybe we'll just add here. SDN primarily decouples our control plane from the data plane, right? And that control plane could sit somewhere on a centralized server. NFV decouples the software function from the hardware, right? And that software could be sitting on a server too. So I think these two technologies are not necessarily mutually exclusive, but I haven't worked on NFV, but at least the understanding is that. And Paresh Bhai is here. Maybe you would like to add something on. They are not necessarily mutually exclusive. That's what we feel.
So obviously there is a little bit of confusion in the industry about NFV and SDN for those of you who are not intimately involved with the two. And you know, they kind of started off pretty independently, right? So NFV really came about in late part of 2012 when a bunch of operators got together and they wanted to come up with a mechanism to move away from purpose-built platforms to having an architecture where they could run these network applications on what we call industry standard servers, right? So the intent at the time was to take the actual application out of these boxes, right? The appliances that we have today, firewalls and packet gateways and even routers and NAT devices and so on. So take the actual application out and be able to run it on an x86 server, right? So that was the point of NFV. So you can see that that's what we're trying to show here is that the intent is take this closed platform, a box that does both of them, the software and the hardware, and where the software and the hardware is very tightly coupled, right? You cannot actually separate it. Vendors do not expose that. I mean, like, you get a box from Cisco, Juniper, Huawei, Nokia, wherever. You can't write your own code and run it on the hardware, right? It doesn't work. And so what we wanted to do, or what operators wanted to do from that perspective, was to take that away and go to a model where the software is actually running in a virtualized fashion, right? So virtualized as in it can run on any standard hardware. And so they buy this commodity off-the-shelf hardware, run the software on it. So that's NFV, right? And a plug for my tutorial tomorrow. So if you want to show up tomorrow, I'll speak at length on it, 3 hours actually. So if you've got that sort of time, come over. SDN. So do you have the SDN picture here? Just before that, right? Okay, you don't. But anyway, so with SDN, what we're doing is a little bit different, right? It's not SDN's not talking about decoupling software and hardware, but what it's saying is that we take some elements of this software, which is the control plane elements, and centralize it. Some, but not all, right? As Tashi has described. So they're kind of different use cases. But so this was the premise on which the whole thing was built. But as time has gone on, we've realized that these are kind of interrelated, right? So to build NFV infrastructure, you kind of end up with a network that is very dynamic, right? You've got these services, these applications, these network functions being instantiated in different parts of the network dynamically. So when that happens, you need to be able to communicate between them, right? And so the technology that's most suited to doing that is SDN, right? So essentially, with SDN, the network can follow the applications and allow them to talk together. So there is a fundamental difference between the two. Does that make sense? Any questions? If you have questions, guys, just call out, because otherwise this will be a very boring session. So, okay, Tashi, on to you.
Thank you, sir. Listing out few of the open source, there are many, I think, open source controllers out there. The first early one, Snox. Then there was Beacon, which was again built by the guys from the OpenFlow project. Then we have the most widely used ODL, Open Daylight controller, right? We have RIU, we have OpenControl. There are many. I have only played with Open Daylight so far, so I do not have the authority to tell you what other controllers behave like. But the idea is pretty much the same, right? Being able to manipulate or insert flows down into the device. But what more could we do, right? OpenFlow is a protocol, right? It acts as an interface between my control plane and my forwarding plane. So OpenFlow is a very rigid, fixed protocol, right? Of course, based on match and actions, as a controller, I'm able to push down flows into the table, right? And whenever the device actually receives a packet, it parses the packet headers, finds a match, and based on the match, it acts, right? So it's based on. All good? Sorry. Yeah? So it's based on match and actions, right? So instead of us just manipulating the forwarding plane, can we actually start implementing this on the hardware itself? Right? The vendors may not want us to do it, but it gives us, from a performance point of view, it would be really nice to be able to actually do that on the hardware itself instead of over a protocol, right? So can we do that? There are lots of research work going on in this field. There is the stock of RMTs, reconfigurable multi-table switches. Currently, all our switches work on a multi-match table concept, right? You have multiple tables on the hardware, on the forwarding level, and then packets get pushed, flows get pushed from one table to the next depending on the matches, right? You have pipeline stages, but the problem is it's fixed. Even though it's multi-match, it's a fixed multi-match concept, right? Vendors, they define small number of tables. The number of tables are fixed. The size of the table and the number of entries that the table can have are pretty much fixed. And even the execution from one table to the next is pretty much fixed. Right? There is no way we can manipulate them. Right? Limited flexibility. And even the actions that we can perform based on a match are also limited. Right? For example, we can, maybe based on a match, I can forward a packet. Maybe based on a match, I can drop a packet. I can tag it with VLAN IDs, or I can encapsulate it under different tunnel headers. Right? Pretty much limited. And when I was talking to a few seniors in Australia, they told me that probably the way we young network engineers think, we are limited, or we have been groomed to think the way we think probably by vendors, the way they want networking to work. Right? Therein comes the idea of having a reconfigurable multi-match switches, right? MMTs. The match fields should be modifiable. We should be able to modify the match fields or add new ones based on our needs, right? Instead of having a fixed set of match fields out there. So we call it the reconfigurable parser, right? Match table sizes also should not be fixed. We should be allowed that flexibility to how many tables I want, or what should be the depth of the table, how many flows it should have, right? And I should be able to define new actions based on the matches. Some of the actions, all these actions, most of us know because that's all the device can at the moment do. Maybe there are. Sure. Sure. And then based on those, some of those actions could actually place the packets on specific output queues, right? So that kind of flexibility, can I get it, right? And that's from the hardware point of view. And the language which could actually help us, P4 is becoming quite the language that people are talking a lot about. I don't know much about P4, but like I said, this talk is not about, this is based on our understanding of what is out there, and we have tried to consolidate this and try and make sense of what it is, right? So P4 is programming protocol independent packet processors, right? P4, a language that actually lets me program. Yep. Yeah. For managing. Mm. Yeah. Hmm. The worry. Hmm. I think it's a very valid thought, right? But I really don't know how to answer that question. But that's why when we were looking at everything that is out there, and if you looked at the framework that we were talking, it's actually if you look at the framework that we were talking early, BGP, right? I need to be sound. I need to know how it works because I think this is where there is a bridge required between folks who are very good at programming things and folks who are very good at maintaining an infrastructure network. I am not a good programmer, but I do script a few things whenever I need it. Only that, right? Yeah. So, but I'm very comfortable with BGP, right? I'm comfortable with how network stuffs work. So maybe I don't know. There needs to be a bridge between folks. Uh,
It- OSPF, yes. BGP, yes. But just add to that a functional programming language to that resume, and it's good, right? I mean, that's where we're going. I think as network engineers, it's not enough anymore just to understand how to CLI, how to BGP, how to do all that. It's a functional programming language is going to be required, and it could be Python, but it could be Go, it could be Java, it could be anything. Just one.
yes, Paresh bhai.
Jeff, right? Thanks for that. I'm of the same view, right? If you look at the skill set that's going to be needed to operate networks in the future, it's a lot different. So none of the core datacom networking skills go away. So we'll still need that. So that's going to be the bare minimum, right? You're going to need to know your IGPs, your OSPF, your BGP, RSAPT, MPLS, and all that. That doesn't go away, but you've got to build systems knowledge on top of it, right? So SDN, like we said, is one part of it, NFA is the other, and both of them require that knowledge. So now you need to have people who understand a bit about virtualization, about server technology, about storage networking, about DC networking. But as a bare minimum, yeah, you've got to have some knowledge of programming, right? Because this is SDN is about programmability, so adding that to it. Now, is it easy to find people like that? No, it's not easy. In fact, that's probably the single biggest challenge facing operators today. The technology is there, right? But to transition from where we are to networks of the future, we'll need to take our organizations with us, and it's challenging. So a lot of this is about education. So some of what we're doing here in Apricot is about making people aware of it, right? So that they know what skill sets they need, because this will not be easy. Now, there's one more thing I must add to it, right? Some of what you see here is an outcome of the industry as a whole, right? So if you look at some of the giant players like Google, like Facebook, and so on, they've been talking about technology in a very different way. What like the small medium kind of operator would think about, right? So these guys, they write their own protocols, they build their own hardware, So they're operating at a completely different level. So you've got to separate some of these web scale companies from your standard operator, because they were a usual sort of telecom operator will not have that know-how desire to do all of the things that the likes of Facebook and Google do, right? So some of the things that Tashi spoke about, P4 and all that, you probably never touch it, right? But it's there. So the idea here is to give you a bit of awareness about that. You don't need all the skills, but you do need to elevate your organization to a higher layer where your people can span both the IT, the traditional IT, and the networking domains. Does that help?
So basically, we need well-rounded folks. Glenn Turner from Osnog was telling me that we need engineers. We don't need network engineers or software engineers, but he feels it's time we had engineers. So maybe that's what Jeff and Paresh were saying, right? And where was I? Yes. So the main goals of P4 was the controller being able to define how a packet is processed or how a packet headers or header fields are passed, right? Reconfigurability in the field. And we shouldn't be limited to known packet formats because the current packet formats are pretty much based on the network protocols that are out there, right? So shouldn't be limited by those. And I could have, of course, most things already do pipeline of match and action tables. So protocol independence, not depending on network protocols to tell us what kind of packet formats to define. And the controller switch needs to know, there is no need actually with the P4 for us to actually know what the underlying switch hardware is. It's more like any programming language that we have. When people develop their programs, they don't necessarily need to understand what the hardware is. It's the compiler's job to know that. So when you compile it on a separate, compile that program on a separate hardware, it compiles according to that underlying hardware. So there is no need for us to build things based on a specific hardware. Right. A quick comparison between OpenFlow and P4. At least that's what they claim. P4 tells what the switch should do, as opposed to the switch telling us what to do. So because in OpenFlow there is still a compromise, right? P4 uses programmable parser that we already saw. OpenFlow parsing is still based on known fields, known packet headers, right? And OpenFlow match and action is pretty much in series, but with P4 they say it can be either in series or in parallel. The major difference is, I think OpenFlow is a fixed protocol because of the compromise that they had to take, whereas P4 is more a language to program the devices, right? We were trying to think of use cases, and a simple use case, for example, let's have a look at this weird topology. And the requirement here is, let's say, the flow from router 1 to router 4, I want it to take this path, and flow from router 5 to router 8, we would like it to take this path. Very simple requirement, right? Basically, I want disjointed paths, right? With our existing, depending on routing protocols to decide what the path is, we might actually end up with flows that actually share a link, right? That's because currently it's distributed decisions. Every network device makes their own decisions, right? So this, something as simple as this becomes quite complicated or looks complex because the decision making is distributed across all devices at the moment, right? Whereas if we had a centralized controller which has a view of the network, then it's quite relatively straightforward. I could insert a flow which says any traffic from R1 to R4, send it across this, take this path, anything from R5 to R8, take this path. Something as simple as this requirement, right? And for this, Pareshbhai, would you want to do this? This is a real use case from a very large network operator in the region which uses many features of the framework that we discussed earlier. So we thought maybe we will include it here so that you get a fair idea of how people are able to leverage the different features out there. So I'll hand it over to you for this.
All right. So, like Kashi said, this is a real use case that an operator is implementing, right? Just to show you guys that SDN is real, not just something that we are trying to push. So let me just talk you through the use case, right? So this operator has is Autonomous System 1, and it pairs with a couple of other ASs, so AS2 and AS3, and it's got end user customers, right, that it provides internet services for. So within the outside of the network, obviously it uses standard BGP, right, to do peering and so on. Inside the network, it actually uses MPLS. So it uses RSVPTE LSPs. And you can see that, the multiple points of ingress into the network, R3, R4. I mean, the customers could be dual homed and so on. It's just simplifying the topology here. You get multiple customers, of course. And so, the traffic paths within the network, there's a ladder network, but with a sort of cross link between R1 and R4. So what the operator does today is, in order to balance the traffic on these links, right, it uses RSVTE. So depending on whether it's downstream or upstream traffic, most of the time it's obviously downstream traffic. What it'll do is they monitor the utilization of this link, right? And if it finds that it's overrunning, running hot, what it does is they push some traffic onto this other LSP so that it starts using this cross-link, and so the traffic gets balanced, right? So this is a very sort of crude mechanism that they use in order to do that. They sometimes use multiple parallel LSPs as well to load share traffic over these different LSPs. Okay, so where are we? Where is this? Okay. Now, the challenge that this operator has is that, particularly on the ingress point from AS2 and AS3, they've got a problem with traffic balancing, right? Because as you know, we can control inbound traffic in a very limited fashion, right? You can do certain things, but you cannot, you're at the mercy of whoever you're peering with in terms of how the traffic flows. So what they find is that they sometimes have the situations where, they've got multiple links to all of these ASs, right? But there are times when some of these are running really, really hot. And in fact, the cases where some traffic starts getting dropped, while the other set of links is not really running very hot. So they do what any operator does, right? They use things like AS path, prepending, and so on to influence the inbound traffic. Now, assuming that that works, right, then you're able to actually control the traffic. Now, the way that these guys do it is that they monitor link utilization of these links, right? So they monitor link utilization of the aggregate traffic over these links and the link utilization here. Now, once they see that it is actually congesting, what they do is they also analyze data from NetFlow, CFlowD, or whatever, right? Whatever they're using in order to collect flow stats. They analyze it, work out where is the traffic coming from. And based on that, they then put in place some BGP policies to apply ASPath, prepend, and so on for a select set of traffic that is that would benefit from being moved onto another set of links. So today it's a laborious kind of process that do this pretty much by hand, right? They collect this data. The data collection is obviously happening all the time. When the thresholds that are set for these links get exceeded, then they analyze this data to work out what to do with it. And then they set up these BGP policies, apply it, and then it's active in the network. Now, this actually takes them 48 hours today. This is a real network. So by the time they've usually implemented this, the traffic has changed, right? So you're kind of it's the goalposts are shifting all the time here for this operator. So it wasn't really working for them. So I thought, can we use some of this SDN capability in order to do a better job of this, right? So that's one. The second one is, like I said, the internal links, right? So the INNIs or whatever you want to call them. So that is also a challenge for them, right? So for example, traffic from entering R1 and destined for R3 could be congesting the R1 to R3 link. And so they have to now manually force some of the traffic over to another LSP. And traffic steering it's not automatic, right? You've got to to push traffic onto different LSPs, you've got to tell the router what traffic to put onto the LSPs. So once again, that takes a bit of manual effort, and it more importantly, it takes time, right, for this to happen. So what they wanted was to completely automate this whole process, right? So that's one of the things you'll see with SDN. If you boil it down to what SDN means, it's a lot of it's about automation, right? It's about getting from where we are today in an automated to a world where things are happening by themselves. So they said, can we automate this whole process, right, for influencing the inbound traffic and also balancing the traffic over the internal links, right? And the strategy was this: we monitor the link utilization, which they're doing today. We set some thresholds. And these are configurable thresholds on the amount of traffic that you would need to hit in order to trigger this. And once that happens, then we do two things. For external links, we work out how we can manipulate this traffic using BGP, right? So in this case, they're looking at AS path prepending, right? And then for outbound traffic, you could use local pref and so on. Today, it's not a real problem. Outbound is not a real problem for this operator, which I guess is the case for a lot of operators out there. But it's they wanted to do that at the same time. And for internal links, come up with a mechanism to intelligently balance this traffic. So here's the solution, right? So firstly, point number one is we monitor the inbound traffic to AS1 from the upstream peers. They set up these things called threshold crossing alerts. So let's just say it's 70%. Some are more adventurous. They said it's at 80%, 90%, right? But okay, let's just say it's some sort of a number that helps you to react in time. We collect stats with IPFix or CFlow or whatever mechanism that you're using there, NetFlow, and based on that, we automatically create these top N lists. Top N in terms of the traffic volume that is hitting us, right? And that gives us the subnets that need to be manipulated. So that's one. That's got to be automated. Second one is when the TCA, the threshold crossing alert event is triggered, then we automatically create a BGP policy update, right? That goes into these routers, configures them, and does, in this case, AS path prepend to the top N traffic contributors in order to move it off to another link. And so we construct the policy and then we apply it, right? We've got to apply it to the routers R1 and R2. So there's got to be a standard mechanism to communicate with these routers through some sort of southbound protocol. Same thing for outbound traffic. I will not go through this in too much detail. It's the exact same thing, except that using maybe local pref to manipulate that. Okay, so for the internal links, similar sort of thing. What we're doing is we would monitor the link utilization of all these links. I mean, this is sort of stuff that you collect today, right? Like most operators collect these stats today. So we collect all the stats, have a threshold crossing alert, and once again we build these top N lists based on destination prefixes. Now this is something that's a bit different, right? Because collecting utilization or tracking utilization is one thing, but trying to work out what is contributing to that utilization is a different thing altogether, right? So even in this case, what we're saying is that the system has to work out what are these destination prefixes. We work on the basis of destination because that's where the traffic is heading, right? That are contributing to all this traffic, and there's a good reason for this, because once you've worked out these destinations, then what you want to do is do flow steering, right? There's an important aspect or element of SDN systems is that we want to be able to influence where specific flows are routed or how they're routed. So once we know what is actually contributing this traffic, then we can specifically steer those flows over LSP1 or LSP2 in order to balance that traffic. Yeah? Okay, so the way SDN does is, it does all of these things, right? If you look at a summary of all the different elements we need, we monitor link utilization, which we do today. We can do that today. We generate alerts on traffic threshold crossing. We can do that today without SDN. We can collect flow information without SDN. Can we analyze flow information without SDN? Yes, we can, right? I mean, today there's a couple of dudes doing that, right, in this operator network. So we work out the top talkers. Can we do BGP policies? Yes, we do that today, right, by hand. Can we apply BGP policy? Yes, we can, by hand. Can we do open flow based traffic steering? Yeah, you can, right, today. So all of this stuff we can do today. What SDN does is the controller can do all of this stuff and interlink that. So that is the solution here. If we bring all of this together under the same umbrella, right? And I sort of refer back to the model that Tashi put up there of the SDN framework. You see that all of these things form part of that SDN controller layer. It's able to do all of that and basically correlate information between them and influence the actions that are taken by the SDN controller. So if you look at this model again, right, you can see how this fits in very neatly with SDN. So link utilization monitoring is part of the resource management function. The flow information collection analysis part of done through IPFix. BGP policy is part of the traffic engineering. Now, the other thing I didn't touch on is once you created the BGP policy, you've got to apply it to the router, right? How do you do it? You can use CLI, but the SDN way of doing it is doing it in a more programmatic, model-driven fashion, which is use netconf, right? OpenFlow for this traffic steering. So you can see how we take this somewhat abstract kind of SDN architecture and realize a real SDN application that solves a real problem for a customer. So see that, getting back to once again to Tashi's point is that SDN is not just one thing or a set of many things. SDN is any of these new capabilities that help us to automate the network, right, by taking advantage of a centralized controller. So when we have different applications that are using different parts, you need to use all of it, right? As long as you're using some of it, you could say that you are using SDN to solve that problem. I think that's it, right, for this one here, Tashi. Any does that make sense? So I mean, yeah. The operator did not write the code to do this. So just for the benefit of people on the streaming channel, what they did was they used a commercial solution to solve this. You could use open source as well. So we're not spruiking one over the other. If you look at all the different solutions out there, they kind of look similar, right? They converged on this architecture. So they did not write the code, but they're using the capabilities. So very powerful. Any other questions on this use case? Do you guys see an application of this in your networks? Yes? No? Yeah. Absolutely. And this is an evolving field, right? There's stuff happening. But at the same time, you don't want to be too far. You can't say I'm going to wait for this to mature, right? So that's what a lot of operators are doing. They're taking baby steps. Some are a bit more advanced than others, but they're trying to dabble in this, solve some real use cases, right? So when people come to us and say, I want to SDN enable my network, and we go, what do you mean by that, right? So it's take the real problem in networking, and technology helps you to solve that problem. And that way you kind of get your feet wet, understand how this works, and then you're gradually able to expand the use cases that you have in your network.
Should we take a break? Maybe we could take an early break and come back. And then we have one more use case, which is actually from our ISP in Europe who has actually done it. So I got their permission to share how they did it with the team here. Right? So we will look at that use case once we come back, and maybe we will run a simple demo of how using OpenTable net switches, how to push flows down. So that's after the break. So let's come back after the break. Thank you.